So in this video, I just want to touch base on overcounting, and I'm just going to borrow an example from Grimaldi, which is a discrete mathematics book which I used. And let's just start. So suppose that we want to draw 5 cards from a standard deck of 52. Now, how many ways can our selection result in a hand with no clubs? So that's just kind of a long-winded answer or a long-winded way of saying how can we get a hand that has no clubs. So here are the different number of ways. So pretty much all you have to do is take away the 13 cards from the 52 that are clubs. So if we take away 13 from 52, that'll leave us with 39 cards, and these 39 cards will have 3 suits. It will either be diamonds, hearts, or spades. And there are no clubs. So it's as simple as that. It's as simple as doing 39, choose 5. So that's the answer to the first question. It's easy as that. We can select our hand, and the amount of ways, the number of ways that we can select a hand such that there are no clubs is 39, choose 5. Simply having no clubs in the deck. Now, how many 5 card hands contain at least one club? Now, all we have to do here is we just have to take away all the choices, all the different ways that we can make a 5 card hand, and we take away the answer that we just got from the ways that we can make a 5 card hand with no clubs. So all we have to do is find all the possibilities. So that's 52 choose 5. Now this is the all the possible hands that we can actually come up with. 52 choose 5. It includes spades, clubs, hearts, or diamonds. So all the possibilities, minus the possibilities of all the hands that has no clubs, which is 39 choose 5, and that'll give us pretty much, it'll give us this number. So 52 choose 5 is pretty much 2,598,960 minus 575,757, and this will give us pretty much around 2 million ways to make a 5 card hand with at least one club. Now, can we obtain the same number in a different way? So let's just move this diagram that we have here. So can we get that same number in a different way? Now, since we want to have at least one club in our 5 card hand, we'll just select the first club. So the first hand that we choose, or the first card that we choose, has to be from 13 cards. These 13 cards are clubs. So there are that many ways to select a club in our hand. Then the other 4 cards, we don't care what the other 4 cards are. So we just, after picking one card, we have 51 more cards in our deck. So we just pick 4 cards from our 51. And this results in 13 times 249,900. That results in 3,248,700. Now this is something that's wrong. The number here is supposed to be 2 million, but we're actually overcounted by 3 million. So what's actually happening is, taking a look at this example, or these cards that I have here, we're actually overcounting. See, we have these distinct cards in the first hand, but then the second hand, we have the same cards. They're just different order. So this is actually three ways, 3 ordered ways of ordering the same cards, but we don't care about order right now. What we want is, we just want a distinct set of cards where order does not matter. So this is actually one way of this represents one way of how we count it, or pretty much this is one way or one possibility of all the possibilities that are possible. But we actually overcounted it by 3. So that's the problem that we have here. When we're counting one possibility as 3 possibilities, and that's why we came up with 3 million instead of 2 million. Now, you could do it. We could do it this way. We could pick, uh, pick like one club in one hand, or 2 clubs in a hand, or 3 clubs in a hand, and that's what we go through here. So I hope the quality is good enough for this chart that I stole from my book. But yeah, this is the other way to arrive at the same answer that we got, which is the 2 million ways to get a hand. So this is the other way, and what we have here, as you can see, is that, for example, on this row, what we have is we have a 5 card hand where we have exactly 2 clubs, and the other 3 cards are whatever cards that we picked. In this other row, we have 3 clubs and 2 other cards that are random cards that we don't care about, but they are not clubs. So what we actually have to do is we have to take all the cases and add them all up. So we want at least 1 club, right? So at least 1 club means 1 or more. So we could have a hand with 1 club, a hand with 2 clubs, a hand with 3 clubs, a hand with 4 clubs, or a hand with all clubs. So we have to consider all the possibilities. And all we have to do is we have to just take a number of ways to select this number of clubs, so the number of clubs in our hand, and we times it by the number of non-clubs that are in our hand. So I guess it's better to just do it as an example, because I really suck at explaining things when it comes to discrete mathematics. So 13 choose 1 times 39 choose 4. So this is the case where we have 1 club and 4 random cards that are not clubs. And we have 13 choose 2 and 39 choose 3. And again, this would be exactly 2 clubs in our hand, and 13 choose 3 times 39 choose 2, plus 13 choose 4 and 39 choose 1, plus 13 choose 5 and 39 choose 0. So we times these all together, and we could actually use the summation formula or use the sigma notation that we learned to come up with a pretty clever way of defining this whole blob of definitions. So we have the limit is 5, and we start with 1 club. So we just take 13, choose I, which is pretty much from these 13 cards that are clubs, choose a couple of them to be in our hand. 39, choose 5 minus I, because say if we chose like 2 clubs, then we actually want 3 cards. Well, what I mean to say is if our hand has exactly 2 clubs, then then there are 3 cards that we want that is not clubs, but they could be random, just not clubs. So what we actually come up with is, I'm just going to pause the video because this might waste time writing. So here we are, and this is the numbers that we get. So after expanding all these, I don't know, expanding all these equations, we get 13 times 82,251, yada yada yada, and we come up with an answer that is 2,023,203, which is the exact number of ways that we came up with in the beginning. So that's an example of overcounting. What happened was uh, we were thinking, well, using this formula, what happened was we were thinking that like objects were actually distinct. So one possibility was represented as 3 possibilities, which caused the overcounting to occur. And that's the kind of things that I want you to look out for. And yeah, I got this example from my book, which I still have after not doing discrete math for a couple of years. But yeah, that's something you gotta watch out for. And that's all for this video. Please rate, comment, and subscribe. Follow us on Twitter, like us on Facebook, and I'll see you guys again next time. Thanks for watching.